Hello, welcome everyone. In today's lecture, we are going to look at another concept that is related to vibrations of a single degree of freedom system. And the concept is what is called as force transmissibility. Okay, so let me look at what we are going to do in this lecture. So essentially what we are going to do is calculate the maximum force that is transmitted to the support by a single degree of freedom system that comprises of a mass, spring, and damper. So essentially we have looked at mass, spring, damper systems, and now what we're going to look at is what is the force that is being conveyed by the system on the support or the base. Okay, so let's think of the scenario where something like this might be applicable. Say you have a system like this where it is essentially the same single degree of freedom system that you have looked at, but instead of being horizontal, it is vertical. Okay, so if you have a system like this, and then this system is actuated by a force P0 sine omega bar t, what we are interested is finding out what is the maximum force that is essentially conveyed to the support or the base due to this P0 sine omega bar t. Okay? Now, if you just apply a static force P0, the force or the reaction at the base would be just P0. Okay? So essentially, if you have a static force, we know that based on statics, that the reaction at the support should also be equal to P0. But when you have a dynamic force or a time-varying force like P0 sine omega bar t, then the actual force that is being felt by the base or the support could be quite a bit larger. And what we will try to do is derive an expression for that particular force that is conveyed to the base. Okay? Now you might ask, like, why are we interested in this? Okay? The reason that we're interested in something like this is because many times when you have a machinery that is vibrating, it is usually mounted on a foundation, okay, using bolts or some other kind of fastening, right? Now, when this vibrating machinery is undergoing vibrations, it's possible that the amount of force it is conveying to the ground or to the support is quite large. So if you are fastening this particular machinery using bolts, for example, the amount of force that the bolts have to take could be actually very, very large compared to the actual forces that are being applied on the machinery. Okay, so you can think of a motor that is mounted on a base or on a beam, and then if this motor has some kind of an imbalance, then it will undergo vibrations. And then the amount of force that is being conveyed to the base or to the beam on which it is mounted could be quite large. So we are interested in finding out what is the maximum forces that are transmitted to a foundation or a beam on which a particular machinery is being mounted. Okay? So that is the reason why we are looking at this particular system. Okay? Now, to find out what is the force that is being felt by this base here, okay, the easiest way to kind of think about is that, okay, what are the components of this mass, spring, damper system that are exerting forces on the base? Okay, so the easiest way to kind of think of that is that you can essentially take a section here, okay, and then free up the support here. Okay, now if you draw the free body diagram, essentially you have a spring force, Fk or Fs, let me call that, okay. And then you have a force that is due to the damper. These are the forces that are being applied by the spring and the damper on the basement or the support. Okay, so essentially, what we're interested in finding out is that at any point in time, what is the force that is exerted by the spring on the base, and what is the force that is exerted by the damper on the base. That is what we're interested in finding out. Okay, and it is fairly easy to do that because we already know what is the solution for a system like this. So we essentially know what is the solution for the displacement x of t. Okay, that is what we derived in the previous lectures. Okay, now because we know what is the displacement function as a function of time, we know that the spring force is nothing but k times x, and the damper force is nothing but c times x dot. So essentially, the total force that is transmitted to the base or to the foundation is kx plus cx dot. Okay, so just to kind of recapitulate what we have learned so far, I have written out the solution here for the steady state vibrations when you have a sinusoidal activation force. Okay, and that is given by this x of t is p naught over k times 1 by square root of 1 minus beta square the whole square plus 2 zeta beta the whole square. Okay, times of course the time varying part. Okay, so essentially this part here, p naught by k with that term, that essentially is the amplitude of the oscillations. Okay, and that is sometimes denoted by the symbol g. Okay, and this is basically the time varying part. Okay. Okay. Now, just to kind of refresh you, these symbols, beta is nothing but the frequency ratio, which is omega bar over omega n. Omega bar is the acquisition frequency. Omega n is the natural frequency, which is given by square root of k over m. Zeta is the damping ratio, which is c over cc. Cc is the critical damping coefficient, which is 2m times omega n. Another way to write that is 2 times square root of mk. Okay, so essentially these are all things that you have learned. We are just going to use these things, so that's why I have written them out again. Okay, okay. So we actually have the solution for x of t, and all we have to do is find out what k times x of t is and what c times x dot of t is, add them up, and that is going to be the force that is being applied to the foundation. Okay, so as I mentioned, you have the spring force and the damping force. Okay, so x of t is nothing but g sine omega bar t minus phi. So that is basically your spring force here. The damper force, you essentially have to take the derivative of x with respect to t, and if you do that, you essentially get this g cos omega bar t minus phi times omega bar. So essentially, when you take the derivative of sine omega bar t minus phi with respect to t, that is what you get. And of course, you multiply that by the damping constancy. Okay, and again, just to remind you, this g is basically the amplitude of the oscillations. Okay, so it's fairly simple so far, right? Essentially, you just have to find kx plus cx dot to find out what is the force that is felt by the base. Okay, now here there is a little bit of math and there is some manipulation of variables that essentially helps us to get to a kind of a compact form for this f base of t. Okay, so what I have done here is that I have written this kx plus cx dot in this way. And since both these terms have a g that is common, I have pulled that out in this step. Okay. Now, here is a little bit of mathematical manipulation. Okay. Now, if you look at this function, g times k sine omega t minus phi plus c omega bar cos omega bar t minus phi, it is not clear what is going to be the maximum force that is going to be conveyed to the system. Okay, because it has both a sine term as well as the cosine term. Okay, and it looks a little bit complicated. Of course, you can take the derivative of this with respect to t and then set it to 0 and so on. But there is a little bit of a mathematical manipulation that we can do that will help us essentially find out what the maximum force that is applied to the base a little bit more simply. Okay, so that's what we're going to do now. So what I'm going to do is I'm going to define a term cos psi as k divided by square root of k square plus c square omega square. Okay, and if cos psi is that, then sin psi is going to be this. Okay, and that essentially you can get using the fact that cos squared psi plus sin squared psi equal to 1. Okay, that is how you get that. Okay, now what I have done is after I define this cos psi and sin psi, I essentially pull out the square root of k square plus c square omega square out of both the terms so that I essentially get terms like this. Okay, and terms like that. Okay, so this essentially comes from that equation. Okay, now if you look at this particular equation, this term here is nothing but your cos psi, and this term here is nothing but your sin psi. Okay, now if you look at the form of this expression, it is of the form sin A cos B plus cos A sin B, which we know is sin A plus B. Okay, in this case, A is omega bar t minus phi, and cos B is basically cos psi, or essentially B is psi. Okay, so if you make this manipulation, what you can do is you can write this f base of t in a very compact form. Okay, so f base of t becomes g times square root of k square plus c square omega bar square times sine omega bar t minus phi plus psi. Okay. Now, essentially, we have separated out the amplitude term and the time varying term. Right? We know that the maximum value of sine omega bar t minus phi minus plus psi is going to be 1. So essentially, the maximum value of this term is 1. So the maximum amplitude is going to be nothing but g times square root of k square plus c square omega bar square. So that is the maximum force that can be transmitted, or that is transmitted by the single degree of freedom system onto the base. Okay, so there's just a little bit of mathematical manipulation that kind of helps us see the amplitude a little bit more clearly. Okay, now once you do this manipulation, we can actually go and make it a little bit more simpler. Okay, so here what I have done is essentially I have taken this term. Okay, let me just erase this. So essentially I have taken this term, g times square root of k square plus c square omega bar square, and then substituted the value for g that is already known, which is nothing but this p naught over k times 1 over square root of 1 minus beta square the whole square plus 2 plus 2 zeta beta the whole square. Okay, that is nothing but your g. That is your g. Okay. So now, once I have this, I'm going to do a little bit more manipulation. What I'm first going to do is, I'm actually first going to take this k inside the square root, and if you do that, that is what you get. Okay. And then you can do a little bit more manipulation. So if you look at this term here, c square omega bar square by k square, okay, you can write it as this way. Okay, again, these are all just mathematical manipulations. So, if you want to skip it, you can also do that. But essentially, if you do these manipulations, what you will end up is that this c square omega bar square by k square, which is this term here, essentially is nothing but 2 zeta beta the whole square. You can show that very easily. Okay. Now, once you see that, things start to make a lot more sense. Because if I can replace this c square omega bar square by 2 zeta beta the whole square, then all the terms in my amplitude of force is going to be essentially composed of just beta and zeta. That's it. Okay? So if you do that manipulation, eventually you end up with a very, very simple formulation for the amplitude of force, which is P naught times square root of 1 plus 2 zeta beta the whole square divided by square root of 1 minus beta square the whole square plus 2 zeta beta the whole square. So essentially, you need to know what is beta, which is the frequency ratio, which is omega bar by omega n, and you need to know what is the damping ratio, which is zeta, which is c over cc. Okay, and that essentially can give you the amplitude of the force that is transmitted to the base during vibration. Okay, now the point of writing this amplitude of force in this particular manner is because it clearly tells you what is the effect of vibrations. Okay, so if you think about this, this P naught is basically the amplitude of the force that you apply. Okay, so if you think about the force, it's P naught sine omega bar t, right? So that is the amplitude of the force that you apply. Now, the actual force that is being felt by the base is not just P naught, but P naught multiplied by this factor, which is called as the amplification factor. Okay, and if you look at the amplification factor, some things become very clear. Now think about a case where beta is very close to 1. Okay, then what happens is that this particular term essentially goes to 0. Right? So essentially, what you'll end up is basically P naught times square root of 1 plus 2 zeta beta the whole square by 2 zeta beta. Okay, and what we know is that zeta is usually very much less than 1. It's actually, often actually less than even 0.1. Okay, so this value is going to be very small. Okay, so for example, and this term is going to be approximately equal to 1. So what you are going to have is that the dynamic force that is being felt by the base is going to be some P naught divided by a factor of say 0.02 or something like that. Okay, something that is very, very small. So effectively, even though the amplitude of the force that is applying is only P naught, the actual force that is actually felt by the foundation or the base could be 50 times larger. Okay, so that is the reason why we need to worry about force transmissibility. Okay, again, this might be a little bit counterintuitive. You might say that you're not even applying a constant force, you're actually oscillating the force, right? You're applying the force like this one at some point and that the opposite direction in some other point. So you might think that the force that is being felt by the foundation should be close to being zero. Okay, on an average, it's zero. But at some instance in time, the forces can be very, very large. And that is what is given by this expression here. Okay, so that was the reason why we need to worry about force transmissibility. Okay, with that, I will end this lecture, and then we'll look at an example using these concepts in the next lecture.